Blackboard. It should be down under the little schedule. There should be a link to it. And then the links to the 2015 classes are still there, and others, so you're always welcome to watch any of those. And then some of them are probably been in there and you've looked at that, you've seen that there's some other little videos that kind of follow along the notes. Some of those are cut out of previous class time, and some of them I did just like I did last weekend with it, talking to myself, which is, so hopefully those are helpful, because as you see, I kind of like to use class time to do more group questioning and problem solving. So we'll do little mini lectures here and there, as you've seen, but I do expect you to have looked through the notes and kind of watched as many of those, and then come to class with questions. So it's totally good to come with questions. And so one thing first is that your assignment is due on Sunday. I'm sorry for that confusion, because I had it Thursday first, and then I was like, realistically, I'm not going to look at it between Thursday and Sunday, so why not give you guys that extra time? And apparently I missed a few places where I had originally set it up for Thursday, so sorry about that. But it is due Sunday night, and if you guys have any questions after class today, I'm happy to answer any. Tomorrow I should be around, but best to kind of email me and find out where I am if you want to sit down and go over anything. Any questions right now?
I missed the first part you said about the video you post, or was notes for second part?
So the one from Tuesday did
record.
It did mostly record,
Okay,
except
yeah.
for the little bit that
It ended.
that nicely caught when it stopped.
Okay.
So there was a bit missing, and I don't know how long that was, but it caught most of it. Yeah, and then the other thing I said is just that there are a few short videos kind of scattered among. It's all within that date readings list that's under each unit. And then the older videos from older class time are down below, but except I think I left the 2015 there. But most of the key videos will be in that little readings section. And I think that's it in terms of logistics for the moment. Any questions you guys have right now? Okay, so what I want to do today, I want to talk a little bit about just the overall problem solving technique. There's the last little bit of chapter 1 in the notes. It's just a couple pages about that, but this is something that we'll come back to multiple times, so I'm just going to do a quick overview on that, because you will see it in many different ways. And then we're going to dive more into the conservation of mass, and mostly for now thinking about conservation of mass in one dimension. And we'll do a little hands-on playing around with M&Ms to create advection and diffusion problems or models. And then a student last year actually took the M&M project and created a little MATLAB script to show what it looks like in MATLAB. So we'll show you that after we've kind of played around with it ourselves. Yeah, what I wanted to just touch on, and I think you've talked about this a little bit in multiple ways, but there's kind of a general approach to almost all geodynamic problems, and a few things that I don't think we've really specified carefully. On Tuesday, we talked about the stuff that we had in our volume that I called phi, and the way that we express this, and we talked about before how you can have stress at a point, and then you can have stress can vary through space, and so any of these geophysical concepts, processes, properties, a lot of this stuff can be distributed in spatially in a body. So this fee can have some amount at all positions within our body. And we call, so this fee could be velocity, it could be stress, it could be the amount of salt, it could be, you name it, you can come up with something. Sometimes you might assume that whatever that property is the same everywhere. Sometimes it's a property that's changing, like velocities sometimes might be changing through time. Velocities can also have a pattern, but be stationary through time. So, you might have a box where things are moving faster over here and slower down here, but that pattern will be steady through time. So this becomes important when you think about solving a problem that is what we call steady state versus non-steady state. And we'll get into this a lot more next week when we get into the conservation of momentum. But steady state doesn't mean that everything is stationary. Steady state just means that the patterns of motion are steady through time. You can also have a steady state salt concentration, even though the salt is generally higher on this side and generally lower on this side. This idea of a spatially distributed XYZ distribution of your property is called a field. So you might talk about the velocity field, or you'll talk about the stress field. And what that's just saying is it's acknowledging that this property changes throughout the system that you're looking at. And so rather than just saying, if you just talk about the stress, then the person you're talking to doesn't necessarily know if you're talking about stress at a point or stress averaged over the whole thing or this or that. But if you specify something about the stress field, then they know you're talking about that pattern of stress as it's distributed. The stress field changes through time. That means that this pattern is changing through time. So that's just some good concept to know about, because most of the time what we're trying to figure out in geodynamics is we're relating a bunch of these fields. We're relating the stress field to the strain field. We might involve a velocity field. We'll have a viscosity field, because we have to understand how the viscosity might be spatially distributed, if that's going to affect our stress-strain relationship. So most of what we're doing is figuring out how to relate all of these fields of whatever it is we're thinking about, whether it's a plate and plate tectonics, or a river flowing, or many different things. So what this means is that your approach to solving the problem will really come down to, and I list it here as kind of seven steps. The first one is really making sure you know what the question is, because just because you're dealing with a river, say, is moving really fast, you might be able to solve the problem just by conservation of mass. You don't need to bring in the movement, the momentum, and all of which is a much more complicated mathematical problem. So you need to make sure you know what the question is, because you might be able to solve it much more simply by making some assumptions and using conservation of mass, say, than in a different situation where the question you really is going to require conservation of momentum. For example, Andrew, you were at Allison's talk yesterday. I think anybody else was. Allison is this visiting faculty member, and she came in with this question about how rivers affect the terminus of a glacier. We think about ocean calving glaciers and lake calving glaciers, but we don't usually think about river calving glaciers. And she was thinking that she was going to have to do this, full momentum solving, figuring out the flow of the ice, and then figuring out how the water carves it away, and that's what she came in with in her head, but then as she described it to this whole group of people in the audience, a few people were like, well, you know, you can actually solve this just using a relatively simple version of the conservation of energy, and conservation of mass together, and you don't have to deal with conservation momentum at all. And so she walked out probably being able to solve the problem with, on one sheet of paper or a handful of lines of code, because it's basically energy in, energy out. How does she estimate those two? They're not that hard. Making sure mass gets conserved along with that energy, and she could be done with like a first step at answering this question in an afternoon, maybe. It might take a little more than that, but but then the next level, so she publishes the first paper with that simple version of it. The next paper she might write starts to look in a little more detail at what's happening, and then she might go to a two-dimensional flow line model that would just start getting at a hints of the full flow behavior of the ice, and then, you know, coming up with a way to describe the water flow and its effect on the ice, and adding some more of the detailed processes in. But you never want to jump straight to the super complicated solution if you can answer the question that's right in front of you with a simpler version of it. So the question, understanding what the question is and not jumping too far ahead of what really is right in front of you, is probably one of the most important skills to practice and to try to think about. Like, what's the super simplest way that I can solve this? Given the specific question that I need to know. So once you understand that, then you can start thinking about, well, how are you going to define the geometry of the problem? What is, you know, yesterday Allison went from thinking about a glacier flowing down into a river like this, which was kind of her first thought of the geometry of her problem. And when she walked out an hour later, she was like, well, what I really need to do is figure out the drainage pattern of the Mississippi River during this time period and estimate the spatial area that water takes up. So the geometry of her problem changed completely when she realized that her question could be solved quite a bit simpler in a different way. So sometimes you will go back and forth and kind of iterate among these. Because whether you define your geometry first or you start to pull together some basic assumptions, and then figuring out which conservation laws you need. Sometimes these three, all of them might kind of bounce back and forth. In this case, after the discussion, we discussed her initial geometry, we discussed a few assumptions, then we got to the conservation law, and we're like, well, it's much easier to do this with conservation of energy than thinking about the full flow. So then she went back and she redefined her geometry and redefined the assumptions. So there's definitely going to be some back and forth on this. The assumptions, as I talked about Tuesday, is something that I'm a real stickler for in terms of all of the papers that you write, like writing out a list of your assumptions, even if they seem super simple, because the best papers out there that are written have the assumptions clearly defined. The reviewers won't get on your case by saying, what do you mean here? How did you come up with this? And justifying those assumptions is just as important. So you can state an assumption. I'm going to assume the density of this table is 10. Great. Why? What citations are you going to put? What are you basing that assumption on? So in addition to stating all of your assumptions clearly, you also have to justify why that's a valid assumption. And usually it's not that hard to if it's a good assumption, then it's not that hard to justify it. But you do need to, and you don't have to give me citations and stuff, but just if there's any reasoning behind your justification for an assumption, then it's great to see that written out. assumptions. And we will, over the next several weeks, go through each of the conservation laws, and hopefully you'll come out of here with a basic understanding of what each is most effective for, and be able to kind of think through, well, what conservation law will help answer my question, because that's kind of a tricky part. So then step 5 is to really basically set up all of the equations. So you'll have a differential equation that'll be your conservation law. You might have 2 differential equations. There'll be partial differential equations. You'll have boundary conditions. Does everybody know what a boundary condition is? We'll talk about these a lot. So whenever you have, if you're going to apply, say, conservation of mass onto this glacier, you actually need to know, well, what's your upstream boundary, and is there a net input of mass up there, and how are you going to specify that? Do you have melting or ablation of the ice on the top, which would be a net output, and that's on your boundary? So you need to carefully define what's happening on every boundary so that you know how to figure out your conservation of mass there. So you'll set up your differential equations, you'll apply your boundary conditions. And boundary conditions are almost always also assumptions, because you are deciding what goes on those boundaries, and that means that it's an assumption you're making. It might be a relatively standard assumption that is made very, very often. And in which case you just say that your assumption is, for example, fluid flow on a hard surface. A very common assumption is that there's a no-slip boundary, that the molecules of the fluid are stuck to the table. The first molecules of the fluid are stuck to the table, and the next ones can move a little bit. So you end up with a pattern of flow that is where the velocity is 0 right on the table and increases outward. This is the bottom of a river, the side of a river. You probably all have noticed that the side of a river, the flow slows down and goes to 0 for the most part. So no slip is a very common assumption. It's common enough that you need to justify why you're applying it, but it's common enough that it's usually pretty easy to apply. For our stress to strain kind of assumptions, so if what we've been doing in terms of the first unit of just understanding what stress and strain mean, that actually all comes down to the conservation of momentum, relating the stress to the strain. So we'll get into more complicated versions of that next week, but if you define your geometry, you make some assumptions about the stress in the system, you state what your assumptions are, including like what the viscosity and the material properties are. You set up your conservation of momentum, which might be a simplified form of that. You set up your boundary conditions. Then you stick in the other equations, which are like your constitutive equation. I'm not writing that very well. This is basically that viscosity. This is often sort of the general form for what we might call material properties. Equations of state are a type of constitutive equation. This could be the ideal gas law or something like that. And so part 6 is where you actually stick in the rest of your equations, and then 7 is you take your solution from combining these two and reinterpreting that solution in terms of the question that you have. So 7 is taking your solution and interpreting it in terms of your question, so that you can explain to the person how you solved the question this way and why this is the right answer to the question. These are just kind of my 7 steps. There's no standard version of, there's no, this is,
It's usually 10, no?
or 12, we have 12-step program. So I like the number 7, so we get 7.
Hello,
So,
I'm a grad student.
what's that?
Hello, I'm a grad student.
Right. So we'll come back to this, and if you approach almost every one of the homework problems I give you, and in designing the problem for your, for the problem design midterm, if you think about going through it this way, or what are you trying to get at, what are the assumptions you're going to make? Are you going to use conservation of mass, momentum, or energy? Sometimes you do need to use multiples of those. And just, you'll get to a point where it's sort of like riding a bicycle, it just comes to you naturally. Oh wait, what assumptions am I making? You start filling something out, you'll automatically start listing your assumptions. So it's a good thing to practice. I've read a lot of really horrible research papers where they don't state their assumptions at all, and then you come out more confused at the end than when you started. So it's just good practice, and will help you in the future. Any questions on that? Does that make sense? Cool. Then we're going to so on Tuesday, we talked about the general conservation, law. Oops. Which looks mostly like this. Where we have our body, it's got some normal, it has a flux of something coming out at that surface. We might have a production term inside, and this is our volume V and our surface S. Do any of you guys remember calculus? How can we relate a surface integral to a volume integral? Because right now we're stuck with 2 volume integrals and a surface integral, which makes life frustrating, mathematically anyways.
It's
Take the integers.
the integral of a surface is supposed to be, isn't it a sphere?
Here.
The integral of the divergence of the the divergence of the volume or the
Yeah, you're on the right track. It's the divergence. So if we have a bunch of little specks of something inside our volume, and our specks of something spread out, so we have the same number of specks, they're just spread out farther, then the divergence of the specks, so how much they've spread out is really what divergence means. I mean, it has a mathematical definition, but it does mean you're spreading out of your stuff in all dimensions. the amount that's spread out within the volume has to be equal to the number of specks that have crossed the boundary. Can you visually see that? If we spread these dots out as much as I just showed here, we have to have a certain number crossing the boundary. And unless we change our boundary, but in this case we're not changing the boundary, so we have so basically what's that saying is that the fee that's moving across the integral of the number of fees that moved across the boundary has to equal the integral of the newly diverged fee inside. So the divergence of fee tells us how much they've spread out, but we're just interested in the number of fee that are inside. Just interested in the ones that are left inside. So the amount that go across the boundary is the amount, well, that's sort of has to be balanced by what's left inside. The reverse, this is basically, it's just like saying if you open the doors to a concert hall and a bunch of people stream out, everybody else inside slowly expands to fill the space. And so there's a relationship between what's inside your space and the volume and what went across the boundary. This is called the divergence theorem. So as you spread stuff out, the amount that you spread stuff out has to be balanced by what crosses the boundary. And this ends up being a really important and easy way to take this and convert it into a volume integral, which then allows us to do more useful stuff with it. So we can express this now as a volume integral of the divergence of our Q. Did I say Q? I mean V.
B.
Q. These notes. Oh, I see why. And then you do have to be a little bit careful. It looks now like we can just take the volume integrals away because there's a volume integral in everything, right? You have to be a little bit careful with that because our material derivative here is outside of the integral. So there's certain cases where you can easily do that and there are others are not. So you just have to be careful about doing that, but often you can. And the one time that you can do it is with when you're working with mass, which means that the conservation of mass, we end up getting rid of those integrals. So this is the general form, and if we swap this, I just you won't have to do this much in that class, but just acknowledging the fact that you have to be careful when you can do that. So when you can just get rid of them, but it still makes it easier to swap that. So if we now think of this as conservation of mass, we really want to say that dm dt equals 0. What are the two parts of our general conservation law?
Production and transport.
Yeah. So if we say that mass, so the total mass actually is a volume integral of the density. And so this allows us to use density So we have d dt of the integral of our density. Is our mass. In this case, you can, we have our transport, let's see. You usually don't create, this is our transport. You don't usually create mass inside a volume. And you usually transport it back and forth. This term is allowing for a change in time. This is our velocity. This is actually the material derivative, and it ends up relating to the transport and then the change in time of our mass. So there is this relationship between our general conservation law in that and this, the material derivative. So they start to look the same, but you just have to be a little bit careful in doing this, especially because with mass we actually are integrating the density to get there. So, but you can work through this, and I worked through the steps in the notes to get rid of that volume integral. You convert the volume to a surface to a volume, and then you can convert it to then we can take that time derivative inside the integral and then get rid of all of the volume integrals, which makes it nice. We end up with basically it's this, but the divergence, that the change with density through time is equal to the divergence of the density which moves with the velocity. So there's this has the velocity in there.
The idea of density and velocity it's hard to imagine it.
Well, this is our transport. So mass doesn't move by itself. It moves when you apply it,
Sure.
when you have a velocity related to it. So our transport has to involve the mass times the movement that's moving. Sorry, that's up in this corner.
So instead of doing momentum, you're doing density.
It's density that.
I mean,
that
it's almost momentum basically.
it's getting, because it is getting at the momentum idea. So,
Right.
but this is just the conservation of the mass.
Mm-hmm.
But it does have, we use the density times the volume is also related to the momentum. So.
Why are you using x and t as your field function? If I understand correct.
This one I use, this would be a vector. So then the field function, we actually do use x, y, z, or you can say at a vector, at a position
Okay.
x.
For all the components.
Yeah, so we use 1, 2, and 3 for the local tensor,
Right.
but and this is why we use 1, 2, and 3 for the tensors most of the time, because we use x, y, and z for the bigger spatial patterns.
I see. Okay.
So that allows you to differentiate between those two.
Okay.
Yeah.
Okay.
So the velocity comes into our conservation of mass because of that transport concept where if we're moving mass across a boundary, it has to move with a velocity. And so this conservation of mass is basically a special case of the conservation of energy. I'm sorry, of the general conservation law. So if we write this in our index notation, we had the divergence of rho v. This would be d rho dt plus d rho vi dxi equals 0. So, I want you guys to, if d rho dt equals 0, so we have a constant density in this system now. So a material that doesn't change its density very much. How does this relate to the strain tensor? So hopefully you guys think about that for 30 seconds or so.
Only in the z, why are you not saying anything about x and y?
Is it?
Now I'm using the xi because we're talking about, this is this differential equation in index notation.
Okay.
So the velocity and the density could have a full field, but this equation is true. These, so vi and xi, vi here is the components of the velocity. That
Right.
velocity may vary over the spatial x, y, and z, but it also has vi, it's a vector that has
I understand.
1, 2, and 3.
Is that the partial of rho with respect to z?
So this is the partial of rho with respect to t. So this is,
Okay.
sorry, and this is t, I'm sorry. This is where it did look like
Oh,
it's-
that's fine.
Sorry.
Okay.
So density is not changing through
Okay.
time. Density is constant.
Okay.
So what are we left with? If density is constant, what are we left with? And can you relate that to the strain tensor?
Strain
So
should
think about that to
be
yourself, and then in 30 seconds, talk to your neighbor and see if you guys have come up with anything. And then we'll discuss it. This is
I think strain is zero. Strain is default. Strain is a default. Strain is very little viscosity. Viscosity is deforming due to stress. We have that movement until it's deforming. Deformation is
It's just saying that the
changing
density is not changing over time, but that doesn't mean there's no like deformation. It's just saying that the change in density is a constant 0, so the whole material has the same density, right?
Sure, but I guess it is a but correct. But in the context of tensor,
I don't know, for me it's not really intuitive to think
Yeah.
change in
I
velocity
agree,
times
and it's a function of time, not a
times the
function
density.
of space. So
Yeah.
function of space, I agree.
Usually it's volume
Because it's
versus
function of space, function of time. And to say something about
Strain.
Strain
Oh,
tensor, strain
yeah,
so it would be
so we I think we
Whatever
assume
is
that
coming in
the density
response
is
of
constant
the
everywhere.
Yeah.
Has to be the amount that goes.
The elongation is not half.
So it's just
So
basically
density
changing
is
velocity
over the time.
in respect to
Tensor, then
is
Hmm.
what I'm quite
Somehow-
Change
Position.
like the displacement.
and kind
Yeah.
of in the idea of
X, Y,
what
Position.
you use as a divergent
It's change in
Um,
velocity of the deformation.
concept you said before. Things are not moving out.
Since
Oh,
there's
just
There's no strain. You're not
total strain has to be
There's
equal to zero.
strain
What does that
tensor,
Yeah.
that would be,
So like
Yeah,
I
I know.
can
That's
understand
my
if you
intuition
have
right now,
the
but-
one,
because the strain has to be zero.
I
two,
can see your reasoning
Wouldn't it?
there.
three,
I don't know.
Like
maybe
the
I'm-
couples
maybe I'm
between
missing
the-
something.
Like the strain
that,
tensor.
like, 0 equals
And I will add one thing, that it's a bit
Oh, yeah,
easier
it's
to
equal
relate
to
it to
zero.
strain rate
Yeah.
tensor, but
I mean, yeah, because rate is velocity, and then we're just about the
Velocity. Which means
so let's see, because the strain along these parts has to be symmetric, I think, or maybe that's stress.
or it can be a constant changing of velocity throughout the distance,
Yeah.
which means it is keep like the strain
What is shear strain?
keeps like happening but in a constant rate.
Mm-hmm.
Constant rate of velocity.
okay, let's come back together. Who's got some ideas? How would you write this? Can you write that out in terms of writing out each term? What does it look like? You said that this was 0. Joshua, what does that look like if we write it out with 1s, 2s, and 3s?
I think, in my understanding, so the density should be constant. If we look at the 3x3 strain tensor, and so dvi over dxi is, I think it's like the change in velocity throughout the displacement is constant, so it keeps changing, but it is in a constant rate.
Oh no, it doesn't.
Okay, I think you're on the right track. But can you just tell me what does that equal in terms of if we put all the components in, if we wrote it all out?
It's just
We have 1s, 2s, and 3s in
Oh.
there. Let's just start
Oh
with
well,
that. What is
so
this? We
like-
now have i's.
so we just replace it with 1, 2, 3. It's
Yeah, so what do I write?
like the I think we can put the row aside.
So yeah, we can forget about that now because it's constant.
So it's dv1 divided by dx1 for the 1, 1. Yeah. For the d1, 1. It's dv1 dx. And then we move along. So dv1 over dx2 would be like the same row from different color.
So is that what this equation is telling us? What is this equation telling us? Does anybody want to help him?
So, it's saying that the partial, well, so it's saying that 0 is equal to the partial of v1 with respect to x1 plus the partial of v2 with respect to x2 plus the partial of v3 with respect to.
Right, because there's 2 i's, right? There's 2 i's we always add with 2 i's. If this were I and a j,
Oh, that's an I.
then Joshua, you would have been right. These are 2 i's, dvi, dxi. Maybe it wasn't clear that they were 2 i's. So this equation is telling us this now for a constant.
There's no displacement. Is that right?
There's no displacement. Explain what you mean.
There's no change in velocity of anywhere you go in space.
Well, not necessarily. The the total change in velocity has to be 0, but there could be changes between
The different
Between them.
components.
Right, so the sum of this has to be 0.
Mm-hmm.
But this one could be
Sure,
minus 10, this
sure.
one could be plus 10, and this one could be 0, or, any combination
Right.
of these three that gives us 0, according to this equation.
So but it's the partial of taking the partial of v, that's
The derivative of the velocity.
is the
Just like
acceleration.
That's a time derivative
that is-
of a
If
velocity.
it is, yeah.
But it is a form of acceleration, it's kind
Or
of a
it's sort of
spatial
a spatial,
acceleration.
yeah.
Spatial acceleration.
What did we
Um,
do in the last week? Do you remember the signal on Monday, I guess this was? The signal input that I gave you was a spike in velocity and then another spike in velocity. Do you guys remember why I gave that to you? Like that? It was the only way it would let me give it to you. But what was that representing? I gave you this. So this was velocity through time. How did that translate to a strain? In this case it was a total strain.
Well, it starts pushing for a little bit, so that creates a stress, which creates some sort of strain. And then it goes back.
Right, so the strain here, the total strain looked like this, right? Do you remember that?
For the spring.
So, and if we're thinking about if we just go in one dimension, we have length initial, our length final, and some delta L. And this happens over some delta T, so our velocity here would be delta L. No. Alright, help me with this. The velocity would be the length L. No, it would be delta L. The change
By
in
doing
length.
the
Change in L over change in T. So that gives us meters per second, say. What is the strain associated with this?
change of L divided by the L1.
So the strain is change in L divided by the initial L. Whoops, not the strain, right? Strain. The rate of strain then? Which is basically the velocity divided by a reference length. So the strain rate is the spatial derivative of the velocity. That's the rate, because if you look at the units on this, right, velocity is meters per second. If you divide by your x, then you get rid of this and you end up with 1/seconds, which is a unitless version of the velocity, basically. So it's basically a relative velocity in a sense. That's what the strain rate is, which we can also see how that's related to the strain. The same way we have a reference, but strain is a relative version of length and a length.
Sorry, would you explain it again one more time? Why you can cancel it?
This velocity has units of meters per second. X has units of meters. So
it's
we just
1/2
cancel
second.
that. Um, so if the strain rates are derivatives of velocity, then epsilon dot 1 1
Yeah.
epsilon dot 1 1 equals dv1 dx1. Epsilon dot 2 2 equals dv2 dx2. Epsilon dot 3 3 equals dv3 dx3. What does
Yeah, and
epsilon
then
dot
we
1
know-
2 equal?
Oh.
DV1 over DX2.
Close. You guys have to realize that I never get phone calls. Nobody ever calls me. Sounds like it's somebody from Cambridge, Massachusetts. Maybe it's Car Talk guys.
One of them is dead. So.
I know, so it's only one.
On 1
So
into, so it's dv2 over x1.
So yeah, so you've got, so there's both of these. We have, because we have 2 epsilon dot 2 1, but those are the same because it's a symmetric tensor, just like our stress tensor. So this is actually 1/2 dv1 dx2 plus dv1
Oh.
dv2 dx1. So it's a sort of an average. So if this doesn't look familiar to you, then I would recommend watching the videos that I asked you to watch from Unit 1 again, or read through the notes on the strain chapter. Because all of the same concepts that we've talked about with stress apply to the strain. This is just the one step, extra step that is in that gives you a little more information about the strain tensor. So its relationships to velocities. So if we now say, well, what was our equation back here? dv1 dx1 plus dv2 dx2 plus dv3 dx3. How is that related to the strain rate tensor now?
It's the trace of the.
It's the trace of the tensor. Yep.
Yeah, it's equal to 0.
That's equal to 0. So conservation of mass for a material that pretty much doesn't change its density. So this is for water, this would be for ice, this would be for most of the rocks that we deal with. The density changes are so small in the grand scheme of things that we almost always have this happening. You have to be, there are cases where your density may not be, your density might be changing and that might be affecting things. So you do have to be a little bit careful. For example, snow undergoes compaction. You have to think about density with some materials that we work with in this class. Air, we don't do a whole lot with atmospheric stuff here, but if you do get into the atmosphere, you can't make this assumption. So things get a little more, the math is just different. But a lot of what we do in this class will have very small changes in density, which means that mostly our conservation of mass we can look at as the trace of the strain rate tensor. What that looks like in terms of our fun boxes that we keep talking about is that if we extend our box in this direction, that's E dot and the 1 1, we have to actually narrow it this way, assuming that our third dimension stays the same. So if E dot 3 3 equals 0, we can say that epsilon dot 1 has to equal epsilon dot 2 2. Does that make sense? Squeeze a box this way, it has to stretch the other way. That's to conserve mass. So if the mass,
Well, it's equal to negative 2 2.
sorry, negative, yes. Thank you. Yeah, so this is to conserve mass with our strain rate tensor. This is not true of the stress tensor. The stress tensor is different. That doesn't have a direct relationship with conservation of mass. But this does. This is the divergence of the velocity is dvi dxi equals 0. Good back of the envelope calculations you can do. Do you remember the Thatcher paper where they were talking about they were squeezing the Himalaya basically from the north to the south, and when they got enough GPS data, they realized that there was this bit that was squirting out towards southeastern China. So the GPS had this sort of squirting motion to the southeast coming out, and they didn't realize that until they got a lot of additional GPS data. They thought it was just squeezing and going up, but they realized that there's some mass going out the side. You can get at those back of the envelope calculations by conservation, using this kind of a conservation of mass. If you squeeze it in one direction, it might elevate the mountains in one way, but if your measured elevations aren't high enough, then you could backpedal and say, well, this squeezing doesn't match this squeezing, which means we have to have a leak somewhere in the system, which in that case was rock squirting out into southeast China. Cool. So does that make sense? The other special bit about the conservation of mass is what we call, and this is what we call the Reynolds transport theorem. And that basically just says any of these other properties that we like to think about, that if they're attached to movement of mass, then you can work with them in the same way. So you can use a similar especially if your phi is carried by the mass. So if our stuff phi goes with mass, then we can treat it for the most part in the same way we treat mass. So in this case, we attach phi to that mass. We can keep track of that property of interest because it goes around with mass, and we can do it the same way. So a lot of phis will behave in the same way as mass. So mathematically, this idea that we can take the derivative d by dt that was outside in our original version of our conservation law, for those items that go with mass, we can take our d by dt inside inside our volume integral, and it just makes a lot of the math easier. So in this class, I won't often have you derive this stuff from these first principles, but I do want you to understand these underlying concepts for solving the problems and how to use the conservation laws. So what we're going to do for the last half an hour is do do some 1D, one-dimensional conservation of mass M&M games. And so in one dimension, let me draw this, so we have, you can kind of, the best, or at least what my brain likes to think of in this could be, you could think of this as a road with traffic on it. You could think of it as a river with an amount of water into it. So we have a linear feature, the road or the river, and at every point in that river we have an amount of stuff. So at point x1 we have that much of our stuff S, which could be the depth of water in your river, or it could be the number of cars if it's a multi-lane road or you've got a certain amount. Point x2, you have another amount of your stuff. So in this, what I've drawn here, this curve is just for t at some t0. So this is your initial amount of stuff, water in the river, say. You could at any point generate, so in this is gonna where x is t2. So we're in a one-dimensional system. So if we transport across the boundary in our volume, it's our one-dimensional volume, a transport across the surface means that we put stuff in at the front of our little line, or we take stuff out at the end of our little line. So that's our transport part of the conservation of mass. If in our one-dimensional system we add, say, rainfall, that's because we're really thinking in one dimensions. That's actually not a transport across the surface, because that would require us having two dimensions. We actually just call that a production. So basically that water instantaneously, those raindrops instantaneously are produced at that point X, wherever it rained. So this is, Q is some flux in and flux out at the edges. X0, let's do this, X final and X0. K is our production. And at each step of the way, we're going to have a transport across any sub-boundaries that we choose in our. So we could have a Q1 across the X1 boundary and a Q2 across the X2 boundary. So if we write our conservation of mass, we have the amount of S, our stuff, as it changes through time. What are the transport and what's the transport term? In as the volume integral.
KdV, I'm gonna roll over KdV.
What's
KdV is our production.
Oh.
And I'm just going to put that over here. K is over here. The divergence of our flux.
Yeah.
And what's the divergence of a flux in one dimension? What's the divergence in one dimension?
The derivative.
It's just it's just that derivative. So this is the divergence of our flux, but we can write it as dq ds. Well, or x. right now with Q, if we don't know the relationship between Q and S, we are applying a K. This is our source term. This is where we tell it how much rain is falling, or whatever. We have to have a in these situations, we're just applying a K. It's sort of an something that we're providing. But in order to really get an idea of what's going on, we sort of need a relationship, if we can, between Q as some function of S. So this is an example of this would be that as a river gets deeper, if you increase the depth of water, what happens to the flux of that water down is at that point?
Slow down.
So if you're conserving, then what you're saying is that
Or
the
it's
flux
the
stays
same.
the same,
Right, it's
and
the
the
same
velocity
velocity,
would
sorry.
would decrease in order
Decrease.
to accommodate that. But we're not changing the width of the river. If you just have more water, does it, with everything else being the same, does the water flow faster or slower?
Faster.
Faster, right. So you have more water, everything else is staying the same, it's gotta flow faster. To get that, you have the same geometry of your system, you put that more water in it, it's gotta flow faster. So for the water, actually, it's something like Q is proportional to the cube of the depth. And you can actually derive that based on the viscosity of water and the relationship of, and we'll do that in our conservation of momentum. But you could do it a bit simpler and just say, well, what if the flux is just a direct function of the amount of stuff you have? So more stuff, more flux. Less stuff, more. But what goes in here is not the flux itself, but the derivative of the flux with space. So if Q is related to if Q is proportional to S, then dQ dx, actually this is not if, this is just another way of writing dQ ds, if this is a function of S, times ds dx. So if there is some relationship between these two, we can write that dq dx as dq ds times ds dx. This takes you back to your old days of differentiation. And so in this case, if they're pretty much proportional to each other, then this dq ds is a constant, right? They're proportional to each other, it's always the same. So we can then rewrite this out. We have ds dt plus dq ds dx equals k, but here we're saying that's some constant. ds dt equals some plus a constant times ds dx equals k. So now our change in time, our s looked like this initially. The change in s at some point x is a function of that slope, the local slope, because that material is moving based on the local slope. This c ends up being, it's like a wave velocity. So this is now a differential equation where s is a function of t, s is a function of x, but we can solve it. Given k and given c, we can solve that for s. And what it ends up looking like with a constant c is that s, x, and t equals s naught, which is our original t equals 0, x minus c t. basically means that if this is a constant, then the shape of this S really just ends up moving downstream. It just is translated downstream at a velocity S. Rivers, this is not a constant, so you can't quite assume that. With rivers, this actually is higher, and so have you guys all, has anyone taken a hydrology class?
Hydrogeology.
How fast do flood waves move down?
Been a while.
Like when they announce on the news that the flood is going to hit some city at some day and some hour, it's actually a lot faster than the actual water moves. So it could be some new city in 12 hours, even though the water itself is going to take 5 days to get there. The reason is that if this C is no longer a constant, but is also a function of your flux, where you have like Q is a cubic power of S, then this wave that's translating downstream actually moves faster than the water itself. So the information is passing by. It's a really weird concept that the information that the rainfall happened gets translated downstream before the actual physical drops of water get there. So the opposite of this is probably something that you guys are a little more familiar with, and it's also a little bit easier to do with M&Ms, and that's that what happens when there's a wreck 5 miles ahead of you on a road? What determines when you discover the wreck happened?
Increase in velocity because of other vehicles in front of you.
Right, and so how does that change depending on the number of cars on the road? If you're the only car on the road besides
You'll discover it at the place.
I'll discover it at the place. If there's 25 cars between the two and they're really packed in, or they're moderately packed in, maybe you'll drive a mile before you'll start to feel that information. If it's totally stopped dead, if you're in the middle of big city traffic, you might know almost immediately that there was a big wreck there. So even though no physical object came and told you that wreck was there, you learned the information about it because of the rules, these rules where you're relating the conservation of mass is relating the amount of stuff in one point to the next point based on it's a function of how much is present. So the more present, the faster you can translate that piece of information. So you can send information, that information will go all the way back miles and miles and miles on the road under some situations because of the way it's packed. The traffic people who design highways and stuff actually do solve these exact differential equations. In that case, we actually have a negative relationship. The C value is not only not a constant, but it's negative. It's relative. It's based on it's based on the amount of stuff, but it's also negative, so that the wave is moving upstream, even though all the objects are moving downstream. So the cars are still net moving downstream, but the information is moving upstream. I just think that's a totally weird concept in life. So we're going to do a little game with that. So I think you guys are all visualizing it, but just to kind of get that started, there's a couple of other games that we'll do.
So basically what is passed down as a pressure wave is what?
It's kind of like a pressure wave. Let's just open these up. And it might actually actually be easier if we're all in one line across the table.
So M&M's in my stomach. Same here.
These are ready to be eaten if you want. Depending on how you feel about eating stuff that other people have touched. And we don't have to use all the bags. So initially, you guys are gonna have a few M&Ms. We're gonna try a couple of different versions of it. We can do it. I mean, you don't have to dump them all out. I don't think you might not need all of them for this. So everybody should get like 5 M&Ms. Let's just start with that. And we need to have a source. Can we get you guys to go on the other side because our road is kind of complicated. And then somebody at one end needs to have a source. Do you have additional ones there? You'll be the upstream source.
Said get about 5.
Well, let's start with 5. And so a simple rule could be that, like, as a traffic situation, the road can only maxes out with, well, we'll start with saying it maxes out with 5 cars. No one person can really, if they have more than 5 cars, they can only pass 5 on to the next person. And only if that person has empty space for you to pass it. And so Annie, you're gonna be just passing them and making a pile. So then we might have to do some transfer back. But we'll kind of do this at a regular interval, and we'll just start. The simplest thing is just to go. Everybody's moving at 5 cars. So let's just get ourselves moving.
All 5?
Yeah, let's just go all 5. So Annie, you shove off 5, then you get 5 new, you get 5 new, you get 5 new, you get 5 new, yeah, wait for the next person.
Yeah. So,
We have to wait until.
Wait, and you get 5 new.
and so
Yeah,
just
no,
keep going.
Yeah, so just keep going.
You gonna pass?
He needs to
Yeah, so
someone's
these
rich.
are moving pretty smoothly. Just keep going.
Well,
just
I
just
can't
keep
have
going.
5 more either. Oh shoot.
Anyone ever played the game Spoons?
Yeah.
This is what this reminds me of. Only you're passing one card at a time.
Right.
You can't pass it until.
I'm also
no,
not
just kidding. Just
murdering
kidding.
everyone
Keep
at
going.
the table to grab something.
Oh, your hands were like this. I was like,
Oh, so
Okay, wait. Now we've got a big hole in our way. We've lost our traffic jam.
Yeah,
Keep
there's
going. Keep
definitely-
going. Keep
Yeah,
going.
the traffic jam thankfully is gone.
No, the traffic jam is your brains at the moment. So if I give you an extra, do you have any?
no.
No. Okay. So now I give you.
You can only pass me 4.
I can only
Don't pass me 5.
oh,
What
the
do you do, man?
Four.
What do you do?
But I have 6 now.
So, but he can't pass you those.
Nope.
So
You have to
he
wait.
can only pass you
So-
4.
Oh, this is big.
Yeah, so give that to him.
So you have to wait to know how much to pass to the next person until you see what they have in front of them.
Okay.
Mm.
Give him 5.
Yeah.
Okay. You got nothing. I'm good.
That sounds like you count. Wait.
I like
no,
those
I
because
don't.
they're all different colors. That makes me comfortable. You should give that to me now.
Well, I can't.
Is that
I
not
mean-
So
bad?
this might be easiest if everybody
You can pass
holds
me
their hands
five.
up if they
I
don't have
have nothing.
anything, and then immediately
You can
puts
pass-
hands down to move only when the person next to them has empty
You
space.
can pass it to me if I have nothing.
Oh, wait.
Yeah, you
So
don't have
do
to
I-
wait on him. You just
Yeah.
have to wait
No.
on me.
Yeah.
Do I
You're
pass
only
it,
looking
do I pass
forward.
It all, or
Yeah.
You
not?
pass the she has to max out at 5.
But you can pass less than 5.
Since you're adjusting, I immediately
You can pass less than 5, but no more. The person next to you can have no more than 5.
You're only waiting on me. You're not waiting on him.
Yeah, and don't even look at the person behind you. Only look forward.
What? Oh, okay. Well,
But you have to hold him up and show him. He doesn't know. Yeah.
well, I didn't know he passed the 1 instead of.
Oh, so wait, what? The one got passed?
Yeah, I
passed
can
it
pass
just
less than
the
5.
Oh, you could. Okay, so we got through the traffic. So you
Yeah.
guys aren't. We didn't have a traffic jam then.
There's a jam now.
It's because there's a little bit of a delay. Yeah, wait, because we have a
there's
apparently we
that.
have a bit of a delay.
Oh wait, sorry. Here's 4.
Well, there's 4 to go. You're 1.
Oh.
so it could be 4.
You can go. You can have done it at the same time.
Oh, yeah, I think it's 6.
Well, I was
problem
trying
is
to
the
see. I was trying
delay.
to see how many she had. If she
Well, by the
just had
time,
1
yeah,
or
no, this is
2
okay. So this is the problem. By the time
Do
you
you
look to
want us
see how
to-
many she has, she's already passed the 1.
Yeah.
So maybe wait so that
Until we have 5. Only pass on 5. what
maybe
you're
only
wanting?
pass on 5. If that's the way, because right now we're not creating a traffic
I know
jam.
because we can pass the 1.
Because we pass the 1 very
Alright.
quickly, and it's harder to calculate how many to pass.
All right. So
in
only
one
pass
time.
if you have 5,
Okay.
But really,
which is what I thought we were initially doing. But
mostly
then I
you should be looking at the, if you're able
Let's say
to.
count to 5 before you.
Whoops.
Sorry.
maybe we're just really efficient.
Yeah.
I can only take 3.
So, yeah. So this basically, that information, it took a couple of time steps for that information to travel upstream, but it did travel upstream to you at one point, because you had to slow down in order to get there. So that's that basic concept of the kinematic wave traveling upstream. It's a little bit harder with M&Ms to get the kinematic wave to travel downstream because you have to do more math in your head to get it to happen. But the next thing I want to do really quickly before we leave is a similar idea, but I want you two in the middle to have 20 each.
Of course you do.
Is that already?
There's a couple.
And the rest of you guys have none for now.
15. Okay, this does not count as 1. We'll take 2 more. Okay, so this is my 20.
And those are your 20.
This is
So
my 20.
in this case, and this is going to take a little bit more math, but try to be quick on it. You can move either left or right, but you can only move a quarter of the difference between what the next person has, and you always have to move it in the direction of high to low. So you have more than him.
Mhm.
You have 20 more than him, so you can give him 5.
Okay, so I can only move a quarter of what I have.
Quarter of the difference in what you have.
Oh, okay.
So it's the same thing. You have
Quarter of what I have?
a quarter of the difference
Difference.
in what you and he has.
Oh, okay.
And
So I can keep doing this though, right?
so the next time step you can
Well,
keep
so I
doing
have
it.
4. I give him 1.
Exactly. So now the next step is that you
15,
you can give a
4, it's
quarter.
11. It's a quarter of 11. Two.
Yeah.
Approximate
Two-ish.
two-ish. Okay, 2-ish. Go.
Okay,
what do
so
you what do you give?
I gave him.
One,
Oh,
But-
oh, and you gave a quarter. Okay. So
Yeah, so you
now
gave a quarter, so now
14 plus 3, 17, a quarter.
Five.
Decimals, you have to chew it.
Yeah, you have
Right,
to
seven.
chew it in half.
Or 8, so that's 2.
Is it 2?
Well, I'll give you 5.
You give me 5 again.
I was thinking 7.
Okay, so there's a
we'll
little bit of
round-
noise
we'll
in
round
the
that
system.
direction, that's
Wait,
good.
you had
Okay, now
13?
you guys go. Yeah, now make
Okay,
sure how
so
close are you guys?
let's
Do you
see.
have
You
about?
have 2.
11. No,
So if you have,
not much of a difference. Still more of a difference between us two. 6. I think I have 11. So, there's
So,
five.
quarter
Yeah.
0.
11,
So
6.
5.
so you can give
So I
her.
give you like
You
1.
can give her 1.
Or you can
You're
go
you're
either
starting
direction.
to average out.
Yeah.
to
Yeah,
a
you can go
quarter,
either direction.
Oh,
say.
2.
Well, I gave you. You
and
just
7.
accumulated them.
So
Yeah.
what's happening here? This is.
Math's happening here. Division.
This is the process of diffusion.
Oh,
So
that's
you have a
fancier.
rule that defines how much you have compared to the both people next to you, and you will diffuse at a rate that depends on that difference. So it'll diffuse. If I gave you guys 50 each, you would immediately give 25. No, 50, 12 to your neighbor. So you can move things a lot faster when it's a steeper gradient. But then as you get down now, it's like, well, okay, so I'm moving one here and one there, and because there's much less of a slope between any two of you. And that's comes out of a lot of these same ideas. There is a diffusion is where your flux, this is not exactly, you can add there's another related term in there, but basically the flux and the direction that you're moving stuff depends on the slope between the two. So if the difference, so d M&Ms over dx, 1/4 of that is kind of I mean, you could have it be anything, but 1/4 is actually the maximum you can do, because you would end up, if you sent too much over, then you could get to a point where you would be creating an instability in our mathematical model here. So if you handed 25, if you had started with 20 and you handed all 20 over, then suddenly he would have to handle all 20 back, and you would end up with this weird, basically that's a mathematical instability, because the diffusion, you can't have diffusion. There's a limit to how diffusion can act in a system like that, and it'll create these, it just doesn't happen. There's a name for it, I have to look up but anyway, this kind of a concept is what diffusion does, and it basically works by looking at the slope between the two spots and then transferring the amount of stuff, so your flux, it then depends on the slope between the two. So in this first case, the flux dependent on the amount, so the flux depended on how many M&Ms you had in front of you. But in the diffusion case, the flux depends on not necessarily how many you have, but how many more you have than the person next to you, or less. Do you guys see the difference in that? So the flux is related to the total amount of M&Ms, and in the second case, the flux is related to the gradient in M&Ms, the slope of your M&M magnitude. And you can see what this looks like quickly. This is too small to see. Diffusion. Okay, so this, Doug Brinkerhoff made this after this puzzle, after I gave him this assignment last year. So he started with 50 M&Ms in the middle, and he had 50 people in his line. And he added a little bit of randomness to choose which time step, which side would make that action. But this is basically what you guys were just doing. And you can see that it gets slower and slower and slower, and the reason that it slows down is because these slopes are no longer very steep. Steep slopes, and you can get a lot out. It's like hot to cold, super hot to super cold. It's easy to imagine that that's changing its temperature really quickly in there to try to equalize things out. The same thing, in the diffusion process, the movement of whatever it is a function of the slope, the immediate slope on either side. The process of advection that we'll get to in more detail is in next week with the conservation momentum, is basically just what you were doing earlier, which is simply transporting. So this is now the M&Ms live in a world of a constant velocity, assuming that it's got a constant velocity to it. So there's a constant background velocity. There, you can even make it a little bit of a so this one is another this one is another version of the velocity, but it goes through a fast velocity zone in the middle. Do you see that?
Mhm.
They jump faster and then they slow back down again. So this is the simple process of advection, which is literally you're just moving the stuff through the system. Diffusion is pulling it out like this. So we'll definitely get into diffusion or advection more. The conservation of mass has that diffusion term in it when D, write it out here. So if the flux is some function of just S, that's the first problem we did. But you can also have the flux be a function of some function of the derivative of S. So, and then you can add them together. So if you have diffusion and advection happening at the same time, it's not as easy to add those in this little discrete model, but yeah. Any last questions?
Can you send the code for any of them? I'm just interested in how to
yeah,
do.
I will definitely. I'll post those.
So it's basically plotting and then replotting on top of that same plot.
Yeah,
Uh-huh.
cycling some little for loops and you guys are welcome to take the M&Ms if you want. I'm not going to eat them. Put them in your cup level. It's dirty.
Are you saying your hands are dirty?
Just clean M&Ms. I'll throw out whatever nobody else wants.
Are you gonna work on hardware?
Joshua. So, in the remote sensing building, there's a planetary lab, which has a giant whiteboard. And Lindsay and I are going to go there.
When?
Now.